Right. You okay, Gina? A bit tired?
Oh, boy.
I'm very tired. So.
You boys? Tim, what are you doing, man?
Loser. Alright. Physics, materials, Hooke. Oh, you probably need that on, huh? It might help a little bit in the teaching.
Yeah, just a bit.
Like this? More? Did we just make it perfect for you? There we go. Okay, Hooke's law. What was the last thing we did yesterday?
The real force against extension.
Oh, the graph, yeah. Oh, this graph.
Yeah.
This one. Okay. Right, so now on to some terms you'll need. I think you know them, but it's good to write them down. So elastic, when we say elastic, what we mean is the material obeys Hooke's law.
Sworn Hooke fealty.
What? Huh?
It has sworn fealty to Hooke.
Yes, indeed. It's one of Hooke's pirates, or what would you call them?
Yes,
Okay, so what do you think plastic means?
it does not.
Yeah. It's a defector. It no longer follows Hooke's law. It's a traitor. Okie dokie. Yeah. Yeah. Elastic limit. What's that now?
The point where it goes
Yeah.
from elastic to plastic.
Yeah. The point where the material is no longer elastic and becomes plastic. Got that? Yeah. Yeah. Okay. Right. Now, a mass M is hung to an elastic material which is suspended from the ceiling, or maybe the mass sits on top of a spring. In both cases, the situation is the same. A mass at the end of a material that is obeying Hooke's law. So I want to look at the first case. Imagine you have a spring that follows Hooke's law, okay, and you attach an M at the end of it. And then what you do is you pull it down, you let go, and it starts going up and down. Right? My question then is what's the formula for the T? And that will equal... Now, I used to do the proof, but I don't do the proof anymore because it's quite difficult and it's not on the exam and it's not in the lab report, so there's no point in doing it. But it can be proven with a bit of effort. It's 2 pi root m over k. That is the formula for the periodic time here. Now, what's nice is it's also the same if it's like this. So if you pull this down and release, it will go like this. Okay? And if you pull this up or push it down as well, let's say we push it down again and release, it'll go like this. Okay? In both cases, believe it or not, and I kind of find it a little bit strange, in both cases the formula is the same. And you might think being upside down might affect it. It doesn't actually. I find that very interesting. What formula does this kind of look like? It looks a bit like the pendulum formula, doesn't it? Doesn't it? You know, 2 pi root L over G. It's not a million miles away from it. So what happens to the time if the m increases? What happens to the periodic time? Increase. And if the stiffness constant of the spring increases? Decrease. Yeah. Okay. What do you think about this third situation? If you have a wall and you have a spring here and there's no friction, everything is smooth again and it's obeying Hooke's law, and you do the same thing. You pull this out, release, and it starts to go back and forth. Again, quite amazing. The formula is still T equals 2 pi root m over k. Quite amazing, I think, that it doesn't really matter which way it's positioned. Yeah.
T is for
The periodic time, the time for one oscillation.
Why does the orientation not matter?
Again, sadly, the proof. If I could show you the proof, you could kind of see that it doesn't matter about the orientation. But the proof is a little bit difficult and a little bit long for us. Essentially, the gravity has no effect on its motion. It still oscillates about an equilibrium. The only effect the gravity would have is where that equilibrium is, but it does nothing about the time. So for example here, this natural equilibrium length would of course be different if you turn it upside down. Which would be bigger? Which equilibrium position is bigger? The top one or the bottom one? The top one, yeah, because it tends to hang down, whereas in the bottom one it kind of sits on top of the spring. Okay, but that changing of the equilibrium position doesn't affect the oscillation time, so it just doesn't affect it. Okay, can I continue? Yeah. So we have this formula. Note the absence of amplitude and natural length, and that's actually what I was just discussing with Zach. The position of the equilibrium doesn't do anything to the time. This is a little bit like in the pendulum. Doesn't really matter the initial angle. The formula doesn't care about it. Okay. Now, what about when two elastic materials are combined, either in series or parallel? How does the K combine? So, for example, imagine you have a spring. Yeah, we'll call it K1, and you stick on the end of it another spring, and you call it K2. So basically what you've done is you've made one large spring. But what is the K for this spring? Okay, so we'll have to...
Doesn't it depend on the length of each of them as well?
No, just the K is... the formula is this. Now, maybe I'll try and do the proof, but I always forget the proof. So I'll try to do the proof. Not that the proof is on the exam. Okay. You got that?
I know that's how they're using some car suspensions.
They stack the springs up.
There's a longer spring for the first few millimeters of travel, and then towards the top there's a spring with a higher spring rate, and then it's more stiff at the top. So it's
So the K's, I'm only talking about how the K's behave, but I would really hope that the natural length of the combined spring depends on the two natural lengths to begin with. So perhaps for the engineer, it's important what the final K and the final natural length is, you know.
But it's not constant throughout.
What's not?
Okay.
No, it's not. But we're putting the two springs together and imagining it's now one spring.
Oh.
So it's almost like the spring is in a box and we care not for internal behaviour. We're basically saying, Zach, if you could combine K1 and K2 to make a new spring, a single spring, it will behave like a spring with what value of K?
Yeah, 1 over K1.
Well, let's see. I'm going to try and prove it. Now notice I've said I'm going to try and prove it because I always forget the proof and then I look it up on Google and then I go, oh, of course. So we'll try and prove it anyways, okay? But maybe you shouldn't write it down in case I make a dog's dinner of this. Right. Let's see. So here, if I pull here so that I get a force backwards here of F, that F will equal Kx. And here, if I pull here, so this pulls back with a force, that force will equal K2 X2. And then here, that F will be the same as that F. And that F is K1X1. So I have K1X1 equals K2X2, which equals Kx. And I also have X equals X1 plus X2. So X is F over K. I'm doing it. X1 is F over K1, and X2 is F over K2. So anyways, yes, 1 over K is 1 over K1 plus 1 over K2. You don't need to write that down. I just feel happy with myself that I could prove it. Okay? So that's the first one. That's if they're in series. All right? Okay, parallel. Any guesses on what the formula would be if they're in parallel? Yeah, go on, Gina. Yeah. K equals K1 plus K2. Will we try and prove it? Sorry, will I try and prove it? Let me try and prove it. Okay. So if they're in parallel, they're lined up like this. Yeah? It's like you have them side by side. And here you kind of need to make sure the lengths are the same because otherwise it would tilt. So you can kind of picture perhaps you have some hook here and this is attached to the wall maybe. You know, something picture like this, okay? If I pull this with a force, this guy will want to pull back with F. Okay? So if I combine these two and imagine them as a single spring, and I pull here, this will pull back with an F. The force here will be Kx. The force in this one will be Kx as well, K1X1, and this one here will be K2X. Yeah? So I have F equals K1X plus K2X. And here F equals Kx. And these are supposed to be the same picture. So we get Kx equals K1X plus K2X. So I can cancel the x's and I get the formula K equals K1 plus K2. Do you know, I'm very happy. This is the first year I proved this without making any mistakes, so I'm quite happy with myself. Right, so that's the second formula, k equals k1 plus k2. Now, two things. Number one, these formulas are not in the formula book. Number two, in the last 12 years, I've only seen this in the exam once. So I think it unlikely you would need these formulas in the exam. But just in case, here they are here. But they're not in the formula book. So I don't know. I ask questions, but I don't get answers. That is in the formula book. Alright, continue. Yep. Right. A rubber band has a natural length of 10 centimetres and a spring constant of 1 Newton per metre. And the rubber band is stretched to twice its length. How much force is required? I'll give you a few seconds. Can you tell me what you get here? Using Hooke's law. Why is everyone taking out their calculators as if you need a calculator here? What's the answer? 0.1. What did you multiply? You multiplied 0.1 by 1. Yeah? 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 Okay. Let's actually do a hard one now, a harder one. A spring is hanging from a ceiling. The weight is 2 kilograms. And you extend it by 5 centimetres. What is the K? So let me draw this for you. You have a spring. It has some natural length. Then what you do? Yeah, you hang, what did I say? 2 kilograms or 5? 2. You hang it 2 kilograms and the result is it extends by 5 centimetres. And my question is, what must the K be? Again, you need Hooke's law, but I'll give you a little hint, okay? In this picture, it's in equilibrium. It's stable. So the force here is what type of force? Gravity. And then the force up here is what type of force? Hooke's. And the relationship between them? Good, okay, give me the K, so. Big enough, yeah? Okay, so Kx equals mg. Right? So K will equal mg over x, which you got is 392.4 newtons per metre. Okay, are we happy with that example? Yeah? Okay, next. A spring with constant 2 is attached to the wall. A boy pulls at a distance 10 centimetres. How much work was done by the boy? So what formula do you need here? This is the half k x squared formula. Do we know the k? Yeah, do we know the x? Yeah, so tell me the work the boy did. No.
0.01.
Yeah, 10 millijoules.
0.01.
Yeah. Did you all get that or not? Gina, you got it or? Yes is okay or it's not okay? Are you sure? I can trust you? Okay. Lynn? Dorian?
Times 2 times
Yeah.
1 squared.
Yeah. Okay. A rubber band is attached to the ceiling. A 100-gram weight is hung on the rubber band and it extends 5 centimetres. So far, this is like the example we did earlier with the 2 kilograms. The weight is pulled down 4 centimetres and released. How long until the weight reaches its maximum height? So, Oh, I don't have my rubber band on today. So what you have is you have your rubber band, and then you come along and you put a weight on it. And the weight causes this to go down 5 centimeters. What can you calculate knowing this? The K. The K. And then someone comes along and pulls it down 5 centimeters and then releases. And it starts going up and down like this. And I want to know what is the time to go from the bottom to the top. You have to half your T. Yeah. Now, this is more like an exam question. The other ones were a little too short. So I'll give you a couple of minutes, see if you can get the time, and then I'll do it. Yeah. Should be a short time. Okay. Let's have a look. So at the beginning, this 0.1, the force up should equal the weight, right? Like in the earlier example.
Yeah.
So you can get K equals mg over x. That's 0.981 over, what was the extension?
0.05.
5 centimeters, isn't it?
0.224.
Yeah. So what did you get for K?
19.62.
Say again?
19.
Thank you. So the time the boy pulls it down and then it snaps back up, the time you want to go from bottom to top is half a period.
So it's just
So it'll just be pi
root
root m over k, which will be pi root 0.1 over 19.62, which equals 224 seconds. Now that's more like an exam question. That's more what I would expect to see in an exam. Okay, is that one okay or not okay? You got that, Dorian and Zach. Lynn, you don't look too happy.
I just can't remember what is.
Because that T formula gives you the time to go from here up and down.
That's one.
But I only wanted the time to go from here to here. So, Harry, is this okay? Are you sure? I can trust you?
Yes.
Oh, good. Okay, you all have that? Now, are you guys still doing homework or what's the story?
I'm still catching it up.
Oh, Zachary. Dorian?
Didn't find problems.
Because you didn't do any?
No, I didn't. I didn't.
Okay, how many did you do?
7.
Oh, good. Gina, last night, did you get any of those latent heat questions done? A few of them, yeah? How many do you think? Good, okay. Lynn? Really? I can trust you? Oh, of course I can trust you. Harry,
Which topic?
the latent heat yesterday. You did them all? How many were there?
Usually only 10.
Oh, okay, sorry. I thought there was like 20. Any problems?
Christian
7, okay.
catching up.
Oh, is that code for I did 0?
No, I did like 3 or 4 of them.
Okay. Zach, how many would you say?
I don't do any of it. I'm still doing.
Okay. You don't want to use a euphemism like Diego, like I'm catching up, or there's still more to do, or take your pick. What could, yeah, okay. Did you hear that, Diego?
No, what?
All right. Okay. So Harry, thank you. You did them all, and he said 7 is a problem. So what we'll do is I'll do number 7. Then I'll give you a few minutes to try some Hooke questions, and then we'll go on to the next lesson. Okay? So let me just close this and open up a tutorial video.
I just have a question.
Which one?
So, why in the equation of Hooke's law,
Yeah.
distance is expressed by x and not s?
Oh, it doesn't matter. Sometimes I use delta x. Some books even use e for extension.